Assalamualaikum, welcome back. Okay, today I'm gonna show you two theorems where we can use double integral to find area of a region, and another one is where you can use double integral to find volume of a solid. Okay, now let's look at the first one first. Okay, let's recall what we've learned in high school, where you can use integration to find area under a curve. Okay, remember when you have y equals f of x. Now let's say you want to find the area under the curve, say from A to B. Okay, if you recall, that would be area is equal to f of x, integrate with respect to x, and let's say x is here from A to B. That would be area under a curve, this curve. That bit there. Okay, so now I'm going to show you how to get the formula here, just to refresh your memory. Okay, first of all, what we do is we partition the area under the curve into rectangulars. Okay, so for example here, I'm going to partition this into a few rectangular. Okay, many rectangular up till, let's say here. Okay, so here we have one rectangular, one rectangular, one rectangular, and one there. So let's say I'm gonna need more space here, so I'm gonna delete that. Alright, so here we partition into rectangulars, and let's say the width of the rectangular is the same, so I'm gonna call this delta x1, delta x2, up till, let's say here is delta xi, up till delta xn. Okay, so let's say we want to find the area of this one rectangular. So area of that rectangular would be the width, which is delta xi, times the length. So the length here would be fx I. So that would be area of this shaded rectangular there. So if we want the area under the graph from this line to this line, what we do is we sum the rectangular, the sum of all the rectangular. So we have fxi, delta xi, I from 1 till n. But that is not really accurate, because then we have we have approximately equal to. Okay, because here we have this gap there, so it's not really accurate, but it's approximately equal to. But to make things more accurate, what we do is we make the width here very close to 0. Okay, very close to 0. So if it's very close to 0, then the number of rectangular that we're gonna have is gonna be a lot. So we take the limit of this as n goes to infinity. So if the width is very small, then the number of columns or the number of rectangulars that we have is going to be approaching infinity. Okay, so then we can change this to equal, and we can change that approximate to equal. And then according to the Riemann sum, okay, so summation, limit of the summation as n goes to infinity can be replaced by integration. And then here we have fx, then delta xi will be replaced by dx. So that would be area under the curve. So just like the formula that we use in high school. Okay, so that would be area under the curve. Alright, so now we can extend this to using two variables instead of one variable. Okay, so now let's say you have a region on an xy plane. So here we have x, y, and then let's say we have a region R here. So this is our region R. Okay, and we want to find the area of that region. Area of that region. So we're going to use the same concept as before, but now instead of rectangular, we're going to partition this into a few squares, or okay, you can say rectangles, but it's going to be smaller. So we're going to partition this into, oops, Oh my goodness. Okay, hang on. All right. So we're going to partition this into a few rectangulars. Okay. And yeah. There. Up till a lot there. So so we have pick one. Let's say here. So let's say this is delta xi, and that is delta yj. Okay, so the width here is delta xi, and the length here is delta xj. I is from, let's say this is from d delta x1 up till here delta xn. Okay, so delta xn. Here is delta x1, and here we have delta y1. Oops. Y1 up till delta yj, and then hang on, so now change that to delta y, let's say m. Okay, all right, so area of that, oops, change color, so area of that one box there is going to be the length, which is delta xi, times the width, which is delta yj. Okay, so if we want to get the area of the region, area of region R, which is the whole thing, so what we're going to do is we're going to sum. So it's going to be approximately equal to so we're going to sum up all the rectangles, delta yj, delta xi, I from 1 till n, and j is from 1 till m. But it's going to be approximately equal to, not exactly. So to make things more accurate, what we're going to do is we're going to make the delta xi, the width, very, very small, close to 0. And also delta yj here, very, very small, close to 0. Then it will be more accurate. So if we do that, area of R is going to be equal to, so we're going to take the limit. So here we have oops, j is going to be from 1 till m, I is from 1 till n, delta yj, delta xi, and the limit is n is going to be infinity, m is going to be close to infinity as well, because we take delta xi and delta yj very, very small, close to 0. Okay, and then according to Riemann sum, this is going to be equal to, so the limit and the summation and then the limit, that will be replaced with with integration. So here we have double integration, and delta yj will be replaced by dy, delta xi will be replaced by dx. So that would be formula for area of region R. Okay, so that is our formula. But of course, you can take dx, dy, or you can also use dx or dx and then dy, or dy and then dx. So for in general, instead of writing dy dx or dx dy, we write it as dA, and the integration here will be over region R, where this is our region R. Okay, and right, and here we have area of region R. So that is the formula that we're going to use, finding area of region R using double integral. So here, that dA can either be dx dy or dy dx. Okay, all right, so back to our note. So here, theorem, I don't number the theorem, but here the area of region R is given by, so area, usually we use A, it's going to be equal to double integration, and here we have R would be our region. So let's say this is our region R on an xy plane, and dA here can either be dx dy or dy dx. So that is one formula that you do need to remember. And we can also find volume of a solid, volume of a solid using double integral, where here fxy is the height of your column. Okay, I'm gonna show you how we get this. It's a similar process. So here, let's say this is our surface z equals f of xy. Alright, so the volume of the solid under the surface z equals f of xy would be the base, the area of the base, multiplied with the height. Okay, so of course the height would be different depending on where you are on the base. So it depends on the point xy on the region R. So here we have we take the volume would be, okay, so we have area of the base from before is dA, area of the base, then multiply with the height. So the height is this, that would be the height. So here that would be the height, which is governed by function fxy. So volume of a solid, which is a solid under the surface, z equals fxy, is equal to this. So this is another theorem, item 2 here. So we have if f is continuous and non-negative on region R, meaning that it doesn't go below the xy plane, that is what non-negative mean, then the volume of a solid lying beneath the surface and above the region R is given by double integration, but now instead of just 1, so here we have 1, but here we have function fxy, where function fxy is really the height of your solid. So we have fxy, when you integrate over region R, that will give you volume of the solid. But if we only have dx dy, which is dA here in general, but it can also be dy dx, integrate over region R will give you area of area of region R. Okay, so we have two theorems there. Okay, you do need to remember this, especially area of region is double integration dA over region R, where dA can be dx dy or dy dx. And this is volume of a solid using double integral, the formula. Okay. Alright, so now we have another theorem. Let's say you have two functions, f and g, okay, and they are continuous in closed and bounded region R. So here you can see that we use dA instead of dx dy or dy dx. So in general, we just put dA. Okay, the first characteristic is if you have a function fxy multiplied with a constant, you want to integrate over region R, you can take the constant out. You can write constant before the double integral. Okay, and here we have linear property. The second case, the second property, if you have function fxy plus g of xy, you want to integrate over region R, this is equal to, so you can partition this into two, integration of f over region R plus integration of g over region R. Okay, and the third, if function f is always larger than or equal to 0 over region R, then the integration of f over region R is also larger than or equal to 0. Fourth, if f is always larger than function g in region R, then the integration of f of region R is also larger than or equal to integration of g over region R. And the fifth is very important. We usually use this quite a lot as well. So let's say your region R is, okay, let's say this is region R, okay, and you want to integrate f of region R. You can partition your region R into two regions, or you can more than that really. So let's say now we partition our region R into S1 and S2, provided that there's no overlap between S1 and S2, no intersection there, and the union of S1 and S2 would be the whole region R. Then the integration of f over region R is equal to integration of f over region S1 plus integration of f over region S2. Okay, so that is the fifth character or property for integration. Okay, so this is quite important, and we use this a lot. 1, 2, and number 5, quite a lot. Okay, now let's go to Fubini's theorem. Okay, here we have a theorem called Fubini's theorem. in Cartesian coordinates. So let's look at the first one. So here, let's say your region R is rectangular. So here we have, we have a rectangular region, okay, like so, meaning that x is from A to B, and here we have the y-axis. Y is from C to D. Then integration of function f over region R here, you can evaluate integration f over region R by either integrating with respect to x first and then y, or y first and then x. So the order of integration in this case does not matter. So if you integrate with respect to x first, then the limit for x would be from A to B, okay, and the limit for y would be from C to D. You can also evaluate this by integrating with respect to y first and then x, but then the limit for the inner integration would be the limit for y, and the limits for the outer integration would be the limits for x. Okay, so that is the simplest region for double integral, where your region R is a rectangular region. So the order of integration does not matter. You can evaluate by integrating with respect to x first and then y, or vice versa. Okay, all right, now I'm gonna show you a much more interesting region. Okay, so here we have another theorem. Here it's called Fubini's theorem on general region. So let's look at the next region. Okay, so here we have region R1. I'm going to call it region R1. As you can see, region R1 is, so here we have the x-axis, and here we have the y-axis. Oops, the y-axis, look at, okay, that's the y-axis. So here our region R is, as you can see, it is between two vertical lines. Okay, two vertical lines. So when we say two vertical lines, meaning that x is from a constant to a constant. So x is from A to B. But then y is from a function of x. Here we have a function of x, and here we have another function of x. So let's call it g1x. And the top boundary is g2x. So here we have our region R. Is bounded by, well, we have four boundaries. On the left, we have x equals A. So this is x equals A. On the right, we have x equals B. On top, we have y equals g2x, so it's going to be a function of x. And at the bottom, we have a function of g1x, so another function of x. So if you want to integrate a function f over this kind of region, order of integration does matter. So in this case, you need to integrate with respect to y first, and then you integrate with respect to x. Okay, so to determine which is the upper limit and the lower limits for y, we just look at the top and the bottom boundary. So the top boundary would be the upper limit for y, and the bottom boundary would be the lower limit for y. So here, limits for y would be g1x to g2x. So the top boundary is upper limit for y, bottom boundary is the lower limit for y. And then you integrate with respect to x. X is from A to B. Excuse me. So this is region R1, where our region is between two vertical lines. So when it's between two vertical lines, you have to integrate with respect to x last. So vertical lines meaning x is from a constant to a constant. So integrate x last. Integrate with respect to y first. Excuse me. Okay, now let's look at another interesting region. So here I'm going to call it region R2. So in region R2, the region is between two horizontal lines. Excuse me. Two horizontal lines, C, y equals C, and y equals D. So if this is the case, order of integration does matter. You have to integrate with respect to x first and then y.